So what I want to do is, remember that I told you that I'm not sure whether the hydrogen is, the energy is being given to the hydrogen, as they say in the problem statement. So I'm not sure, like I said, I'm not sure if there's an energy here going like this, right? I'm going to try to do an energy balance here. If this works out, then all good. So what I can do, there's different approaches here. You can do this and see if it checks out. If this is indeed equal, then there's no energy being given to the nitrogen or by the nitrogen. If this is different, then there is an energy source there. So what I'm going to do is I'm going to relate these guys individually. I'm going to break and see what's happening with the enthalpy, because we know the temperature is decreasing after all, and what's happening with the kinetic energy. And we're going to relate those facts later. Okay. The other thing I can note is that because I have the mass flow rate, I can transform these guys in rates and have it all in watts instead of having it in energy units. So what's happening with my enthalpy out minus enthalpy in? What is that equal to? Well, if I relate that the C sub P is E H dt, and I do the integral here, I'm going to get the delta H equals Cp delta T. This is delta H right here, so this is the same thing as Cp delta T, and therefore all I need is delta T. I happen to know this is 60 and 50, so I can do this fairly quickly. What I don't know is C sub P, and this is something that you can grab off the table, but we don't have to. In this case here, if this were a test, we can find it ourselves. How do we go about doing that? Well, we know that K was given, so let me do in a different color so we can relate this. So how can I find C sub P? Two things. We were given K, and we know Mayer's law, right? So K, as I said, is Cp divided by Cv, and we happen to know this is 1.4 for this case. And Mayer's law says the R equals Cp minus Cv. So if I relate these two things, I can find out what Cp is for this case. And to do that, what I'm going to do is I'm going to divide by Cp here. I'm going to take Mayer's law, divide both sides by Cp. So that's going to give me R by Cp equals 1 minus C sub V, C sub P. And what I can do now is this is 1 over K. So this equals 1 minus 1 over K. And what I can do now is go ahead and multiply back the C sub P from the R. So I'm going to get R equals C sub P minus C sub P minus 1 C sub P over K. Because K is also related to C sub P, I can go once again. Let me think about this. It's probably an easier way to do this. No, I know what I'm going to do. So from here, I'm going to go ahead and, yeah, that's a good idea actually. Okay, so from here I'm going to say, okay, so R equals C sub P times 1 minus 1 over K. What I can do here is say this is C sub P of K minus 1 over K, right? And if that's the case, this is all equal to R, then therefore C sub P is just R, and the inverse of this, which is K minus 1. Okay, so now I know this number here, this is a constant, this is my 8.314. I know this is 1.4, and there's no dimensions there. So as long as this is the right unit, I can relate these numbers here, and that's going to be 8.34 times 1.4. 1.4 minus 1 is 0.4. And unit-wise, I have joules. Not going to do that mistake again. Joules, Kelvin, mole. I need that in kilograms, so I need to relate once again the molecular weight. And I need to say 28 times 10 to the minus 3 kilograms for every mole that I have. So that once again allows me to eliminate the moles, and I'm going to get joules per Kelvin per kilogram, which is great. All right, cool. So C sub P will be equal to 1,039.31, and that's going to be joules per Kelvin per kilogram. Okay, again, if you have a table, you can use it, or if you can use the internet, you can go ahead and do this faster. But in case you needed to do it in an exam, that's how you can go about doing it. All right, so here we're trying to find a delta H. Relating this back, C sub P is this, so therefore my delta H is simply C sub P times delta T. This is outlet is 50, inlet is 60. Celsius or Kelvin, doesn't matter, we're going to have 10 as the difference. And I'm going to be left with joules per kilogram. I don't want that. I want to eliminate the mass. So I know the mass flow rate, so I'm going to go ahead and multiply this by the mass flow rate too. And the mass flow rate here is, what was it? .44. 4.44. So let me do it one step at a time. Okay, so that's just going to be 10, right? That's going to be 10. So that's going to be 3, 9, and then 3.1, right? That's going to be joules per kilograms. And now if I want the rate, let me go ahead and call it. Just put a dot there for rate. Then I'm going to multiply by the mass flow rate. So I'm going to do this big number that I just found times the 4.44 times 10 to the minus 2. That is joules per kilogram. So that gives me 461. Oh, negative, right? This is negative, sorry. This is negative because of this negative here. So this has to be -2. So this is also a negative number. And this is 461.45. So I'm going to go ahead and say 461.5 watts. Cool. All right, this is important. All right, so we're losing. All right, there's energy leaving my nitrogen, given the enthalpy balance. Okay, so again, let's go back to the analysis here. Let's pretend for a second that we don't have the kinetic energy. So in other words, we don't have this or this. Our conclusion here would be this is happening. We have energy leaving this, probably in the form of heat, right? Leaving this system. But we have the kinetic energy to account for. So we need to look at what's happening there to be able to come to a final conclusion. And what does our kinetic energy say? So let's do a little balance on the kinetic energy. In black now. So we have, what is the delta of the kinetic energy? Will be the kinetic energy out minus the kinetic energy in. That will be mass V out squared over 2 minus mass V in squared over 2. What do we know? We know the mass values. I'm going to go ahead and send the masses to the other side. I'm going to say this is delta key E of the mass. And I'm just going to have velocity squared divided by 2. This is outlet is 170 squared. Inlet is 10 squared. Divide the whole thing by 2. This will give me 14.4 times 10 to the third. Okay, and the unit here is, if we were to do this, we're going to get joules, but we're not multiplying by the mass, so this is joules per kilogram. We're still needing to multiply by the mass. So joules per kilogram. Okay, so you can think about the unit, we're doing meters squared divided by seconds squared. It's the same thing as acceleration times distance. That's the same thing as Newton. Acceleration is the same thing as a Newton times Newton times meter is a joule, so that's joules per kilogram. Okay, so now we need to get rid of this mass over here. So if I want to know the rate, I'm going to multiply it by the 4.4 times 10 to the minus 2, and that is kilograms per second, multiplied by the joules per kilogram. And that gives me 639.36. So let's go ahead and approximate that to 639 watts. Okay, so kilograms and kilograms, joules per second, that's the same thing as a watt. So what do we know now? Well, the kinetic energy increased, right? So what's the aftermath in terms of the energy balance? We have, let's come here, we have, due to these guys here, right, there's we have 400 and something leaving the system. Due to these guys here, we have 600 and something entering the system. So therefore, some 200 watts are going into our system. So therefore, it cannot be this situation. What we have is actually this situation. All right. So indeed, remember back in the beginning when I read the problem statement and I said, well, is the energy really going to the nitrogen? Because that's counterintuitive. Well, in fact, it is going into the nitrogen. Right? We have energy going to the nitrogen, and that energy is not being converted into internal energy or energy of the gas because the temperature is decreasing from 60 to 50, but it's going into the gas in the form of kinetic energy because it's increasing its velocity from 10 all the way to 170 meters per second. Okay, so what is the, what's the actual question that we need to answer? What's the rate of heat transfer to the nitrogen? Okay, the rate of heat transfer to the nitrogen will be, back to this idea here, and actually this idea here too. Because the energy balance needs to be 0, that means that everything that's entering minus everything that's leaving has to be 0, right? So what is entering? In plus heat entering minus out, all this has to be 0. Well, we know that H in minus H out, we know that looks like. We also know what kinetic energy in minus kinetic energy out looks like. So therefore, those guys have to be equal to minus Q. What is this? Kinetic energy, internal energy in minus internal energy out in terms of the rate. That's going to be the 400 and this one here is 60, this is 50, so this whole thing is 400 and what was the number? 61.5. What about this guy here? Well, this one is 10, this one is 170, so this is going to be a negative number, and this is my 639. Everything here is in watts. That's going to be minus Q. So therefore, minus Q equals minus 177.5, and therefore Q equals 177.5 watts. Whew. Okay, so because of the first law, the nitrogen gained energy, and this energy must come from some external source of heat or energy that's supplying this to the system. That's our conclusion here. Okay, so like I said, part E is where it gets, interesting, where we start relate the first law with everything else. I hope this video was helpful. If it was, consider giving it a like. If you have any questions, as per usual, just leave them down below, and we'll talk soon.